Now let's see this example about this round robin. See, round robin is bit, I don't say difficult, but you have to be very attentive while solving round robin. The reason is you have to keep track of various things while you are doing this. So first of all, you have all the process arriving at various times. Now what is the first process which is arrived? The process which has arrived, the first process which arrived is at time 0, right? Therefore, I am going to write it like this. Now this is the Gantt chart. I am going to maintain the Gantt chart throughout, first thing, and second thing is along with the Gantt chart I will even maintain the queue. Queue is nothing but the order at which, okay, what is the criteria here? We are going to use two criteria. One is what is the time quantum, right, and along with the time quantum, arrival time. So actually arrival time is used in this just like you know, first come first served. It is a kind of first come first served algorithm, except that first come first served is preemptive, non-preemptive, but here it is preemptive. Round robin is preemptive version. So preemptive version means while a process is still running, while it still wants more time, we'll pull it out and then schedule the next one. And then the arrival time is the same criteria which is used at first come first served. If you remember FCFS, there we used arrival time as the criteria. Here along with the arrival time I use something called as time quantum. Time quantum is what is the maximum allowable time that a process can run once it is scheduled. That is called time quantum. Okay. Now see this. At time 0, if I start it, what is the first process that gets scheduled? The queue. So I am talking about the queue. Now this queue will contain the available, this is the queue and this is the Gantt chart. Now this queue will contain what are available processes in the order of their time of arrival. Now P1 is the first one which has arrived, therefore I don't have any choice, I am going to schedule it. Now once scheduled, every process is supposed to run only for the time quantum amount of time. And how much is the time quantum here? 2. Therefore till time 2 P1 is going to run. Now after it is done, it has to go out and then bring the next process, which means it is supposed to leave the CPU and move it, have a transition from running state to ready state. Now at this point the time is 2. Now check that when the time is 2, by this time more processes would have arrived, isn't it? What are the other processes they have arrived by time 2? Process P2 has arrived and process P3 has arrived. So before doing anything, you add every process which has arrived. See, now the time is 2 at which P1 has stopped, but then don't write P1 here, just write all the process which arrived there. So what are all the process which arrived? One is P2 and P3, therefore I have written them in the same order of their order of arriving, therefore they are in the queue in this order. And now this P1 which has been removed from the queue and put here will now go and stand in the line after them. So next time it is going to get a chance after P2 gets a chance and P3 gets a chance. Understood this? And now what is the next one in the queue? P2. Therefore remove P2 from the queue and schedule it. Fine. Now P2 is going to execute, right? For how long? Now we should check two things. One thing is we are going to execute it for a maximum of time quantum which is 2, and sometimes the process might not need 2 units at all. So if you look at it, the process needs 5 units, therefore it could go and execute for 5 minutes, till the time quantum. So one thing is you should even keep on decrementing this. The reason is process P1 has already executed for 2 units, so in total if it needs 4 units, now the remaining time it needs is only 2 units. Got it? Okay. And now what about process P2? P2 has finished its execution for time quantum, therefore it should go and stand in the queue, but then you should first add 2 units are over, that is why it is 3. You should first add all the processes which have arrived meanwhile. Now what is the time? 4. Now see what are the processes which have arrived meanwhile. So P4 and P5 has arrived. Therefore P4, P5 have to be written in the queue. Fine. And now after writing them, this P2 has to be again sent back into the queue. So P2, that is how you should write it. Okay. And what is the next process which gets scheduled? Obviously the next process P3. So I am going to schedule P3, And now I'll just see if P3 requires the TQ amount of time quantum. Yes, P3 burst time required is 2 and the time quantum available is 2. Therefore I am going to run it till 6, which is nothing but is going to complete. It is going to run till completion, and since it has already finished its burst time, you need not add it in the queue, right? But then meanwhile, just check if any process has arrived by 6. Yes, by the time 6, process number P6 has already arrived, therefore P6 should be written here. And now you need not put P3 here because P3 required only 2 units and we have run it for 2 units, therefore you need not put it back. Now check this. Now what is the next one? P3 has to be removed from here, right? What is next one? Next one is P1 that will get scheduled. And how much does P1 require? 2 units. Yes, you can run it for 2 units because time quantum is 2 units. And now after this 2 units, its requirement is over. I mean, it has run to completion. Therefore, you need not add it back. And what is the next one that has to be chosen? P4. So how much time does P4 require? It is interesting. See this. P4 requires only 1 unit. Therefore, even though it has a chance to run for 2 units, it is saying that I need only 1 unit. Therefore, run it for only 1 unit, which means till 9, right? So it is going to be 0. Got it? Next one is P5, isn't it? You need not put P4 back. The reason is it has run to the completion, right? And next one is P5. P1 is removed from the queue and it is scheduled. Now check this. What is the time quantum required? So P5 requires 6 units and the time quantum is 2 units. Therefore, I am going to run it till 11, right? So how much is remaining? 4 is remaining, isn't it? Time of 4 is remaining, and I am going to run it till 11. And after running it, it will again go back and sit in the queue. Wait for its chance next time, right? And now what is next one? P2. So we are going to take P2, and P2 requires 3 units of time. Therefore, I am going to run it for 2 units of time, which is time quantum. And after that, this is going to drop down to 1. And after that execution, P2 will be again going and sitting in the queue. And what is next one? Again P6 will get scheduled. P6. If you look at P6, it requires only how much? 3 units of time, right? So I am going to run it for 2 units, which means 15. Therefore, the remaining time is 1, right? And again P6 is going to sit back in the queue and wait. Fine. Now what is the next one? P5. So how much is remaining time for P5? P5 will get scheduled, and how long is it going to run? P5 is going to run for 2 units because it requires 4 units, right? So I am going to run it for 2 units. Yeah. So it is going to run till 17. Fine. And after that it should go and sit in the queue, and it requires further 2 more units, right? And what is next one? P2. So if I remove P2 and schedule it, check its requirement. P2 wants only 1 unit of time. Therefore, I am going to run it for only 1 unit, which is 18, and it becomes 0, which means it gets completed. Therefore, you need not put P2 back, right? And what about next one? P6, right? How much time does P6 require? Again, P6 requires only 1 unit of time. So I am going to run it only for 1 unit, which means by 19 it is going to complete, and therefore the remaining time is going to be 0. It is going to be finished by 19. Got it? So you need not put P6 back in the queue. What is the next one remaining? P5, right? Only one process is remaining, and you could directly run it till completion, whatever the time it is. Why? Because even if you run it in terms of TQ, the same process will be coming over and again. So you need not worry about it. Run it till completion. Then what about this? 21, right? So if you count all of this, this is how the process are executed. Now let's see what is the completion time, turnaround time, and waiting time, right? So it is understood why it is complex, because you have to maintain 3 things here. What is the remaining burst time? You should maintain that. And then what are the process in the queue? We should maintain that order, because in that order we are going to select each one, right? And then you should even maintain the Gantt chart. That is why it is a bit complex compared to others. Now writing the completion time. So completion time is a bit difficult in the sense you should see from the right hand side, not from the left hand side, right? So you see where a process is occurring at the last time in the Gantt chart, that is the completion time. Now I want the completion time of P1, right? Now you check it. P1 has occurred last here, and when is it happened? When did it happen? At 8. Therefore P1 finished at 8. After that it didn't arrive any, it didn't show up anywhere, which means P1 must have been completed there, right? Therefore the completion time of P1 is 8. And then completion time of P2. Now again check it from the end. So this is the last time where P2 has occurred, and after this P2 never occurred, which means this must be the time where it finished completely. So it is at 18. So P2 is 18. And what about P3? P3 is, watch it, from the right hand side you should check everything, and P3 has occurred here, right? So the completion time for P3 is 6. After this it didn't occur anywhere, check it. Therefore that must be really completion time. And now if you observe it, P3 has occurred only at one point. The reason is P3's burst time is 2, and therefore once you schedule it, time quantum is also 2, it will run to completion. And next one is P4. Again you check from this side, P4 has occurred only here, right? And its completion time is 9. So you can say that P4 completion time is 9 here. And P5 has occurred here last time, and its completion time is 21. And P6 has occurred here, and its completion time is 19, right? And after finding out the completion time, you are supposed to find out the turnaround time. So what is turnaround time? Completion time minus arrival time, that is the total time spent by a process in the system right from its arrival to its completion, right? And now what is the difference? 8 minus 0 is 8, 18 minus 1 is 17, and 6 minus 2 is 4, 9 minus 3 is 6, 21 minus 4 is it is 17, 19 minus 6 is 13, right? And once the completion time is over, then you are supposed to find out the waiting time. So what is waiting time? This turnaround time minus burst time. So waiting time here is 4, and waiting time here is 12, waiting time here is 2, and waiting time here is 5, waiting time here is 11, and waiting time here is 10, right? And after finishing this, you can find out what is the average turnaround time and average waiting time using the normal method. That is straightforward. So what is the average turnaround time? Add all of them, and then 1 2 3 4 5 6 divide by 6, that is average turnaround time. And average waiting time is add all of them and then divide them with 6, right? So that is how this round robin works, right? So if you observe it, in the round robin, these are all called as context switches. We are going to pull one process out and then schedule the next one, right? These are all called as context switches. Now, as the time quantum increases, the context switches will decrease, or if you have a very small context time quantum, then what happens is the number of context switches, they increase. So I'll just show you with an example what happens if I increase the time quantum. See, if time quantum equal to 2, then we got this all. This is the Gantt chart, right? Now what happens if I increase the time quantum? Then definitely you will see that the number of times I might have to pull out a system and then schedule the next one will decrease. The reason is very simple. Whenever you schedule a process, don't interrupt it at every small amounts of time. That is going to lead to lots of context switches. Instead of that, run it for more time. But then what is the problem of having a time quantum which is very large is starvation. So a station might have to wait for a long time before it gets a chance. If I have 100 processes and if the time quantum is 2 units, then some process might have to wait for nearly 99 into 2 units, isn't it? The last one. So as we increase the time quantum, some process might starve for a long time, but as we decrease the time quantum, we might have lots of context switching. So what you should do is you should come up with a value which is neither too big nor too small. So what I mean to say is, instead of this time quantum 2, if I increase it, I'll have very less number of context switches. Or instead of this time quantum 2, if I decrease it, I'll have more number of context switches. I'll show you what it is. Okay, fine. Now we shall see with time quantum equal to 4. Now let's solve the same one with time quantum equal to 4. If the time quantum equal to 4, let's take the same example and solve it, which means the process number is like this. I'm doing the same one, 1 2 3 4 5, 6, and then arrival time, and arrival times is 0, 1, 2, 3, 4, 6, and the burst times are 4, 5, 2, 1, 6, 3, right? Yes, now let's solve this. So the same way, first of all we are going to maintain the queue. So inside the queue the first process available will be P1 at time t equal to 0. Therefore initially at 0 I am going to schedule P1, but unlike the previous example, here the time quantum is 4, which means I can run for 4 units, right? So I can run till 4 units and then I'll check it. See this. Therefore it is completed. It need not be scheduled again, right? So it will not interfere with the execution next, right? Now the time is 4 and you need not add it to the queue again. By time P4, time 4, what are the other processes which got available? One is P2 and other is P3, other is P4 and other is P5. All these processes became available. Now which one should you schedule next? P2, right? So next P2 has to be scheduled and it could run for 4 units, right? Therefore it could run for 4 units, which means till 8 it could run, and therefore only 1 unit is remaining for it for the next time execution. And now by the time P2 is over, the time is 6. So by this time the process P6 is available now, therefore P6 will be added to the queue. And now even P2 has to be added back because it has still some more need, which is 1 unit, therefore I am adding P2 back. And next one which will be scheduled is P3. So P3, now how much time can you schedule it? For 4 units, but then P3 is saying that I don't need 4 units, I need only 2 units, right? So you can only run it for 2 units and then it is over, finish, right? Therefore P3 need not be added. Next one that has to be scheduled is P4. Now you can run it for 4 units, but just check its need. P4 is saying that I need only 1 unit, therefore run it for only 1 unit and then finish it off and don't add it back. And next one is P5. P5 can be scheduled, right? And now if you schedule P5 can be scheduled for 4 units, but what is its need? 6 units, right? Therefore it is going to be 2 units is going to be remaining, so it will run till 15 because I can run it for 4 units. So its next time its need is 2, therefore you should keep it back in the queue because it has even further need. Next one is P6. P6 has to be scheduled. Now what is its requirement is 3 units only, therefore I need not execute it for 4, I will execute it till 18, right? And it need not be added back. And what is the next one? P2. P2 requires only 1 unit because it already executed for 4 units, right? Therefore it is 19, right? And P2 need not be added again. Then again finally P5, right? So how much time does P5 require? 2 more units, therefore it is still 21, that's it. So if you look at the Gantt chart, it is clearly showing that the Gantt chart of this one is very large compared to this one. So the context switchings are very high here compared to this. So what can you understand? As I increase the time quantum, right, the context switchings are actually decreasing. Context switching is nothing but this line, right? So which means after finishing one process, you are scheduling, after executing one process, you are executing the next one. This switch is called context switching, and here the context switchings are very high compared to this one, right? Why did this happen? Because of time quantum. Therefore see that time quantum is not too small because context switching is going to be very high, and see that time quantum is not too large also. The reason is, if the time quantum is too large, then many of the processes are going to stop. For example, here see this, I'll just show you. Let us say P6. When did P6 get the chance? For the first time P6 is able to run at 15 units. But then if you see this one, P6 is able to run at 13 units. Therefore a process is not waiting for so long, but here it is waiting for too long. And again if you see P5, here first time P5 is able to execute at 11, and if you look at P5 it is able to execute at 9, right? That is the difference. Therefore if the time quantum is large, a process might have to wait for a long time to get its chance, right? So it should not be too large and it should not be too small. So this, now you could find, similarly you can find what is the completion time, what is the waiting time and turnaround time. Just see this. Let's see the completion times. When did P1 get completed? So look at the last time. Actually, P1 got scheduled only once, and that one time is enough because its burst time is 4 and the available time quantum is 4. Therefore, completion time of P1 is 4 and completion time of P2 is 19. This is the last time it occurred, right? Completion time of P2 is 19 and completion time of P3 is 10. Completion time of P4 is 11 and completion time of P5 is P5 is here, right? So 21 and completion time of P6 is here, which is 18. Got it? Therefore, after this you can find out turnaround time. What is turnaround time? Completion time minus arrival time, which is 4 here, 18 here, 8 here, and then 8 here, and then 17 here, and then 13 here, right? See, in any case, if I write any number wrong, you please cross check it. Anyway, I think you are also doing it along with me. In case if you think that some numbers I have written here is wrong, you please correct it, because I'm just doing it, like I'm just doing it while I'm teaching. So it might be wrong sometimes. And then waiting time is turnaround time as burst time. Here it is 0, here it is 13, here it is 6, here it is 7, here it is 11, and here it is 10. So that is waiting time. You can find out what is average turnaround time and average waiting time, right? And you can even see that even waiting time, I think waiting time is not going to be much different. Maybe you can just test out. So what happened to waiting time? Maybe with some examples you will find out that if there might be some difference there. Okay, so this is all about the this round robin with time quantums 2 and 4. Let's solve some more examples on this.